Planet formation is one of the most fascinating topics in astronomy and planetary science because it helps us understand not only the origins of our own planet, but also the diversity of worlds throughout the universe. But before we continue, please make sure to subscribe and leave like for more sleepy science videos. By studying how planets form, scientists can trace the processes that turn clouds of gas and dust into fully developed planetary systems, providing insights into the conditions that make planets habitable or hostile to life. Understanding planet formation also allows researchers to interpret observations of distant exoplanets and their orbits, compositions, and atmospheres, offering clues about the broader evolution of galaxies and star systems. The scales involved in these processes are immense, ranging from microscopic dust particles to planets thousands of kilometers in diameter, which emphasizes the extraordinary complexity of the mechanisms at work. Planetary science addresses key questions about the universe. How do planets grow from tiny grains of dust? What determines whether a planet becomes rocky like Earth or gaseous like Jupiter? How do collisions, radiation, and magnetic fields influence planetary evolution? By answering these questions, scientists are able to construct models that explain the formation of both our solar system and the thousands of exoplanetary systems discovered in recent decades, deepening our understanding of the cosmic environment and our place within it. Stars are born within vast, cold clouds of gas and dust known as molecular clouds. These clouds, often spanning dozens to hundreds of light years, contain primarily hydrogen molecules along with traces of helium, carbon, oxygen, and other heavier elements. Within these molecular clouds, regions of higher density can form due to turbulence, shock waves from nearby supernovae, or interactions with other clouds. When a region becomes sufficiently dense, gravitational forces begin to dominate over thermal pressure and other supporting forces, causing the material to collapse under its own gravity. This collapse triggers the initial stages of star formation, as the cloud fragments into smaller clumps that continue to contract and heat up over time. As the material collapses, conservation of angular momentum causes the rotating cloud to spin faster, flattening into a disk-like structure around the nascent star. This spinning disk, known as a protoplanetary disk, is a natural consequence of the star formation process and serves as the birthplace of planets. The disk itself is composed of gas and dust, with the gas accounting for roughly 99% of the mass and dust representing the remaining 1%. Despite its relatively small fraction of the total mass, the dust plays a critical role in planet formation, providing the solid building blocks that eventually coalesce into planetesimals and, later, full-fledged planets. The structure of a protoplanetary disk is far from uniform. It typically exhibits a dense, hot inner region close to the central star and a cooler, more diffuse outer region extending hundreds of astronomical units. In the innermost regions, temperatures are high enough to vaporize most ices, leaving refractory materials such as silicates and metals as the primary solid constituents. Farther out in the disk, beyond the so-called snow line, temperatures drop sufficiently for volatile compounds like water, ammonia, and methane to condense into solid ice grains. This temperature gradient plays a critical role in determining the composition of planets that form at different distances from the star, with inner planets tending to be rocky and outer planets potentially accumulating large amounts of gas and ice. The density of material in the disk also varies with distance from the star, often following a power law distribution in which the surface density decreases with increasing radius. This distribution influences the rate at which solid particles collide and stick together, which is essential for the initial stages of planet formation. Turbulence and gas motions within the disk are another important aspect of its structure. Turbulent eddies, pressure gradients, and magnetic effects can cause the dust and gas to interact in complex ways, leading to localized regions of higher particle concentration. These regions are critical for overcoming barriers to growth, such as the meter-size problem, where intermediate-sized particles tend to drift toward the star before they can grow into larger bodies. The interaction between gas and dust also leads to phenomena such as radial drift, vertical settling, and concentration and pressure traps, all of which influence the efficiency and timescale of planet formation. Observations using infrared and radio telescopes have revealed that protoplanetary disks often exhibit rings, gaps, and spiral structures, which are thought to be caused by embedded protoplanets or variations in gas density. These structures provide direct evidence that planet formation begins while the disk is still present, highlighting the dynamic and evolving nature of these environments. Chemical composition in the disk is another critical factor. The gas primarily consists of molecular hydrogen and helium, while dust grains include silicates, carbonaceous materials, and ices. The abundance and distribution of these materials determine the types of planets that can form. In particular, the presence of volatile ices beyond the snow line allows the rapid accumulation of solid cores capable of attracting significant gaseous envelopes, ultimately leading to the formation of gas giants. In the inner disk, the limited availability of ices results in smaller, denser rocky planets. Over time, the gas in the disk dissipates due to stellar winds, radiation pressure, and accretion onto the star, leaving behind the solid material that continues to evolve into planetesimals and protoplanets. The lifetime of the gas disk, typically a few million years, sets a critical timescale for planet formation, especially for the formation of gas-rich planets. The study of protoplanetary disks and their evolution has been greatly advanced by modern observational techniques. Telescopes such as the Atacama Large Millimeter/Submillimeter Array, ALMA, allow astronomers to map the distribution of gas and dust with unprecedented resolution, revealing details about disk mass, density structures, and chemical composition. Observations in different wavelengths, from infrared to radio, help trace both the hot inner regions and the cold outer regions of disks. These observations have confirmed that disks are common around young stars, supporting the idea that planet formation is a widespread process in the galaxy. Theoretical models and numerical simulations complement these observations by providing insights into the physical processes governing disk dynamics, dust growth, and gas accretion. In summary, stars form from the gravitational collapse of dense regions within molecular clouds, and the conservation of angular momentum naturally leads to the creation of protoplanetary disks around these young stars. These disks are composed of gas and dust, with complex structures influenced by temperature gradients, turbulence, and chemical composition. The dust grains within the disk serve as the seeds for planet formation, and their interactions with gas and each other set the stage for the growth of larger bodies. Observations of disks at various wavelengths reveal rings, gaps, and other features that indicate ongoing planet formation, while models help explain the physical mechanisms behind these processes. The combination of gas and dust dynamics, chemical variation, and evolving structures within protoplanetary disks provides the essential environment from which diverse planetary systems can emerge, establishing the foundation for the formation of worlds like our own and many others throughout the galaxy. Cosmic dust is a fundamental component in the formation of planets, acting as the building material from which larger structures eventually emerge. Despite its minuscule size, typically ranging from a few nanometers to micrometers, dust plays an outsized role in shaping the evolution of protoplanetary disks and the creation of planetary systems. The composition of cosmic dust is varied, reflecting the processes and environments from which it originates. Silicates, primarily composed of silicon and oxygen, form a major fraction of interstellar dust. These silicate grains can be crystalline or amorphous and serve as the backbone for rocky planet formation. Metallic grains, often containing elements such as iron, nickel, and magnesium, provide high-density material that contributes to the formation of planetary cores. In the cooler regions of protoplanetary disks, ices composed of water, ammonia, methane, and carbon dioxide can condense onto dust grains, significantly increasing their mass and stickiness. These ices are especially important beyond the snow line, where they facilitate the rapid growth of planetesimals and the eventual formation of gas giants. The combination of silicates, metals, and ices creates a diverse population of dust grains with different physical and chemical properties, influencing how they collide, stick together, and evolve over time. The sources of cosmic dust are varied and span multiple stages of stellar and galactic evolution. One of the primary contributors is supernovae, the explosive deaths of massive stars. Supernovae eject vast quantities of material into space, including heavy elements synthesized during the star's lifetime and during the explosion itself. These elements condense into solid grains as they cool, forming silicates, metals, and other compounds that seed the interstellar medium. Another significant source is the winds of evolved stars, such as asymptotic giant branch stars, which expel material enriched in carbon, oxygen, and heavier elements. Interstellar dust is also constantly recycled through the galactic environment, subjected to processes like shock waves, collisions, and irradiation by cosmic rays. This recycling ensures a steady supply of material for new star and planet formation. The interstellar medium, though diffuse, contains enough dust and gas to form entire generations of stars and planetary systems, demonstrating the universality of these materials across the galaxy. The physical properties of dust grains, including size, shape, and surface chemistry, are crucial for their role in planet formation. Small grains can collide and stick due to electrostatic forces, forming larger aggregates, known as pebbles. As these aggregates grow, gravity becomes increasingly important, allowing them to attract additional material and evolve into planetesimals. The presence of ices on the surface of dust grains enhances this process by increasing the likelihood that particles will adhere upon collision. Dust also interacts with the surrounding gas in the protoplanetary disk, experiencing drag, settling toward the midplane, and undergoing radial migration. These interactions influence where and how quickly planetesimals can form and determine the eventual architecture of the planetary system. The chemical composition of dust affects the types of planets that can develop, as certain elements are necessary for forming rocky cores, metallic interiors, or volatile-rich envelopes. Beyond their role in building planets, dust grains influence the thermal and radiative properties of protoplanetary disks. Dust absorbs and scatters stellar radiation, heating the disk and affecting the temperature gradients that dictate where different compounds can condense. The distribution of dust determines the optical thickness of the disk, influencing observations at various wavelengths and providing astronomers with critical clues about disk structure and evolution. Dust also serves as a surface for chemical reactions, facilitating the formation of complex molecules, including organics that may later contribute to prebiotic chemistry on forming planets. The catalytic role of dust in astrochemistry demonstrates that these tiny particles are not merely inert building blocks, but active participants in the processes that shape planetary environments. Observations of cosmic dust in our galaxy and beyond have been greatly enhanced by advances in telescopes and space missions. Infrared astronomy, for instance, allows scientists to detect thermal emission from dust grains, revealing their temperature, composition, and spatial distribution within disks. Polarization studies provide insights into the alignment and shapes of dust particles, while spectroscopy identifies the chemical bonds present in silicates, ices, and organics. These observations confirm that dust is ubiquitous in star-forming regions and that it exhibits a wide range of compositions and structures. Laboratory experiments complement astronomical observations by replicating the conditions of space, testing how dust grains collide, stick, and grow under microgravity and low-temperature environments. Such studies have confirmed the importance of dust in initiating the chain of events that ultimately leads to planet formation. The importance of dust for future planets cannot be overstated. Without dust, there would be no solid material to seed the growth of planetesimals, no surfaces for chemical reactions, and no medium to modulate the thermal and radiative environment of the disk. Dust is essentially the raw material from which all terrestrial planets, the cores of gas giants, moons, and even smaller bodies like asteroids and comets are built. The size distribution, composition, and dynamics of dust grains in the early stages of disk evolution strongly influence the types, sizes, and compositions of planets that can form. By understanding the origin, properties, and behavior of cosmic dust, scientists gain insight into the first steps of planet formation, the diversity of planetary systems, and the potential for habitable worlds to emerge. In essence, cosmic dust is the foundation of planetary architecture, linking the death of stars and the recycling of matter in the galaxy to the creation of entirely new worlds. The initial aggregation of particles in a protoplanetary disk marks the very first step in the long journey from microscopic dust to full-sized planets. This stage begins with the countless tiny dust grains embedded within the disk, which are constantly in motion due to turbulence, thermal vibrations, and interactions with the surrounding gas. As these particles move, collisions occur frequently, and while most are gentle, they are essential for the early stages of growth. The mechanisms driving these collisions are varied. Brownian motion, the random movement of tiny particles suspended in a gas, causes the smallest grains to frequently bump into one another. In addition, turbulence within the disk generates eddies and vortices that can transport dust grains of different sizes at varying velocities, leading to further encounters. Larger particles may experience differential radial drift, meaning they move through the gas at different speeds due to drag forces, creating another source of collision. Even though the relative velocities are low, these repeated encounters provide countless opportunities for grains to interact and, under the right conditions, stick together, forming larger aggregates over time. Electrostatic forces play a critical role in facilitating particle sticking. At microscopic scales, dust grains can acquire electric charges through processes such as friction, ionization from cosmic rays, or ultraviolet irradiation from the central star. These charges create attractive forces between grains, helping them adhere upon contact rather than bouncing apart. In this early stage, the surface chemistry of the grains also matters. Coatings of ices, organics, or other sticky substances enhance the probability of adhesion. Even very small forces, imperceptible at macroscopic scales, are sufficient to bind grains together in the low-gravity, low-velocity environment of the protoplanetary disk. Once grains stick, they create fractal-like structures, forming porous and irregular aggregates that can grow by capturing additional particles. This combination of mechanical collisions and electrostatic attraction allows dust grains to transition from isolated microscopic particles to larger clumps over time, setting the stage for subsequent growth into planetesimals. The formation of microscopic clumps is a gradual but crucial process. As individual grains collide and stick, the aggregates begin to take on irregular shapes with internal voids, which increase their cross-sectional area and make further collisions more likely. These early clumps are typically on the scale of micrometers to millimeters, but their growth is exponential. The more material a clump contains, the higher the probability it will encounter and capture additional grains. In this phase, collisions are still gentle enough to avoid fragmentation, allowing the aggregates to grow steadily. Laboratory experiments simulating microgravity conditions have shown that these clumps can form surprisingly complex and porous structures, resembling tiny cosmic fluff balls that are surprisingly resilient. The porosity of these aggregates plays a significant role in their dynamics, affecting how they settle toward the midplane of the disk, how they interact with the surrounding gas, and how effectively they capture additional material. Turbulence within the protoplanetary disk is both a facilitator and a challenge for particle aggregation. On one hand, turbulence increases the frequency of collisions by stirring dust grains and bringing them into contact. On the other hand, if the relative velocities induced by turbulence become too high, collisions can lead to fragmentation rather than growth. Therefore, the effectiveness of initial aggregation depends on a delicate balance between gentle, frequent collisions and destructive high-velocity impacts. Localized regions within the disk, such as areas of pressure maxima or vortices, can provide favorable environments where relative velocities are lower and particle concentration is higher, promoting the formation of dense clumps. These regions act as natural incubators for the earliest stages of planet formation, concentrating material and enhancing the efficiency of aggregation. The size distribution of the dust grains also influences the aggregation process. Smaller grains tend to stick more easily due to higher surface area to mass ratios and stronger relative electrostatic effects, while larger grains benefit from higher inertia that allows them to sweep up smaller particles. This complementary interaction between different grain sizes accelerates the formation of larger aggregates. Over time, the initially microscopic clumps evolve into millimeter to centimeter-sized pebbles, representing the first macroscopic structures in the disk. These pebbles will later serve as the seeds for planetesimals, but the transition from clump to pebble already marks a significant milestone in the pathway from dust to planet. Chemical and environmental factors further influence the early aggregation phase. Regions of the disk with slightly higher concentrations of volatile ices or organic materials tend to produce more adhesive clumps, facilitating faster growth. Temperature gradients, radiation levels, and gas density all play roles in determining the efficiency and stability of aggregation. Observations of protoplanetary disks in the infrared and millimeter wavelengths provide evidence that these early stages are occurring in real star systems, with dust grains beginning to coalesce and settle toward the midplane, forming the dense layers from which planetesimals will eventually emerge. In summary, the initial aggregation of dust grains represents the foundational step in planet formation, transforming isolated microscopic particles into larger, coherent structures. Collisions driven by Brownian motion, turbulence, and differential drift bring particles into contact, while electrostatic forces and sticky surface coatings allow them to adhere and form aggregates. These microscopic clumps grow in size and complexity, influenced by local disk conditions, turbulence, and grain size distributions. Over time, these clumps evolve into larger pebbles, setting the stage for the formation of planetesimals and eventually fully developed planets. This phase illustrates how even the smallest particles in the cosmos, through persistent interactions and subtle forces, can initiate the extraordinary process of building worlds. The growth of dust aggregates into planetesimals represents a critical stage in the formation of planetary systems, bridging the gap between microscopic grains and kilometer-sized building blocks of planets. Once dust grains have formed millimeter to centimeter-sized pebbles through initial aggregation, they enter a phase dominated by coagulation, a process in which collisions and sticking gradually increase the size of these particles. At these scales, the interactions between particles are no longer solely influenced by electrostatic forces. Gravity begins to play a subtle role, particularly for the larger aggregates. As pebbles collide, they can adhere due to a combination of van der Waals forces, sticky ices on their surfaces, and the dissipation of kinetic energy during collisions. This coagulation process allows aggregates to grow steadily, forming decimeter-sized objects and eventually reaching sizes on the order of meters. However, the pathway from small pebbles to full planetesimals is not straightforward. One of the primary challenges is the so-called meter-size barrier, a term used to describe the difficulty particles encounter once they approach sizes of approximately 1 meter. At this scale, two major problems emerge. First, radial drift becomes significant. Meter-sized bodies experience strong aerodynamic drag from the surrounding gas, causing them to spiral rapidly toward the central star. The timescale for inward migration can be as short as a few hundred years, far shorter than the timescale needed for continued growth by collisions. Second, collisions at this size tend to become destructive rather than constructive. Relative velocities between meter-sized bodies increase due to turbulence and differential motion within the disk, leading to bouncing or fragmentation instead of adhesion. This barrier represents a major bottleneck in planet formation, raising questions about how planetesimals, which are the precursors to planets, can successfully form. Turbulence within the protoplanetary disk plays a dual role in the growth of planetesimals. On one hand, turbulence is essential for maintaining collisions between particles of different sizes, mixing material throughout the disk, and preventing dust from settling too quickly into a thin midplane. Turbulence generates eddies and vortices, concentrating particles locally and sometimes creating traps where solids accumulate. These high-density regions are crucial because they can locally increase the probability of sticking, potentially allowing aggregates to overcome the meter-size barrier. On the other hand, excessive turbulence can be destructive. High relative velocities induced by strong turbulent motion can fragment particles during collisions, resetting the growth process. The balance between constructive and destructive effects of turbulence is therefore critical in determining whether planetesimals can emerge in a given region of the disk. Several mechanisms have been proposed to overcome the meter-size barrier. One prominent idea is the streaming instability, a collective phenomenon in which solids and gas interact in such a way that dust particles cluster together. In regions where the solid-to-gas ratio is enhanced, small perturbations in particle density can grow, leading to the rapid formation of dense clumps of pebbles. These clumps can reach sufficient densities for self-gravity to take over, collapsing into kilometer-sized planetesimals in relatively short timescales. This process bypasses the slow, incremental growth that would otherwise be hindered by radial drift and collisional fragmentation. Another proposed mechanism involves the trapping of particles in pressure bumps or vortices within the disk. These local pressure maxima act as safe havens where solids can accumulate and grow with reduced risk of inward migration or destructive collisions. Both mechanisms highlight the importance of the interplay between gas and solids in facilitating the formation of planetesimals. The physical properties of the particles themselves also influence the efficiency of growth. The composition of dust, presence of ice mantles, and porosity of aggregates determine how likely particles are to stick during collisions. Ice-coated grains, for example, are more adhesive and can survive higher velocity impacts, allowing growth to proceed farther than it would for dry silicate particles. Porous aggregates dissipate energy more effectively upon impact, reducing fragmentation and increasing the probability of coalescence. The size distribution of particles in the disk is another factor, as a mixture of small and large particles tends to facilitate growth through the sweeping up of smaller grains by larger bodies. Observational evidence from young protoplanetary disks supports the idea that planetesimal formation is occurring efficiently in many systems. High-resolution imaging at millimeter and submillimeter wavelengths reveals rings, gaps, and clumps within disks, indicative of regions where solid material is concentrating. Spectroscopic studies of dust emission suggest that grain growth from micron-sized particles to millimeter and centimeter-sized pebbles is common within the first few million years of disk evolution. These observations, combined with theoretical models, indicate that the transition from pebbles to planetesimals, although complex, is a robust process occurring in diverse environments. Once planetesimals reach sizes of kilometers, they become largely immune to aerodynamic drag and can survive long enough to participate in gravitational interactions. At this stage, gravity becomes the dominant force, setting the stage for the next phase of planet formation, the accretion of these planetesimals into protoplanets and eventually full-sized planets. The formation of planetesimals represents a critical threshold. From this point onward, bodies have sufficient mass to influence their surroundings, attract additional material, and initiate runaway growth processes. The challenges faced during this phase, including the meter-size barrier and the influence of turbulence, illustrate the delicate balance of forces that shape the architecture of emerging planetary systems. In summary, the growth of millimeter to meter-sized particles into planetesimals is a complex interplay of coagulation, turbulence, and gravitational effects. Dust and pebble aggregates collide and stick under the influence of adhesive forces, while turbulence both aids and challenges their growth. Mechanisms such as streaming instabilities and particle trapping in pressure maxima provide pathways to overcome the meter-sized barrier, allowing rapid formation of kilometer-sized bodies. Particle properties, local disk conditions, and gas-solid interactions all contribute to determining the efficiency of planetesimal formation. By the end of this stage, solid bodies have reached a size where gravity dominates, enabling them to participate in the next crucial steps of planetary formation and ultimately giving rise to the diverse worlds observed in planetary systems throughout the galaxy. The formation of protoplanets represents a critical stage in the transformation of a protoplanetary disk into a planetary system. As kilometer-sized planetesimals collide, merge, and interact under the influence of gravity to form larger, more complex bodies. Once planetesimals reach sufficient size, typically several kilometers in diameter, their self-gravity begins to dominate their evolution, drawing in nearby material and facilitating accretion. Collisions between planetesimals are no longer purely random events. Instead, they are influenced by gravitational focusing, a process in which the gravitational pull of a growing body enhances the probability of capturing passing smaller objects. As a result, larger planetesimals tend to grow faster than smaller ones, initiating a runaway growth phase in which a few bodies rapidly outpace the rest, evolving into protoplanets. This preferential growth creates a hierarchical structure within the disk, with massive bodies embedded among a population of smaller planetesimals that continue to serve as a source of material for accretion. The process of merging planetesimals is not uniform and is strongly influenced by the dynamical evolution of the disk. Collisions can vary from gentle accretionary events, which result in growth, to high-energy impacts that may fragment the bodies involved. The relative velocities of planetesimals depend on the local density of material, orbital eccentricities, and inclinations. Regions with higher planetesimal density experience more frequent collisions, accelerating growth, whereas more dynamically excited regions with higher velocity dispersions may see collisions that are destructive rather than constructive. Over time, gravitational interactions among planetesimals tend to stir the population, increasing eccentricities and inclinations and affecting the overall efficiency of accretion. Despite these challenges, simulations indicate that protoplanets can form efficiently within a few million years, particularly in regions where planetesimal densities are high and relative velocities remain moderate. Local gravitational resonances play a key role in shaping the formation and distribution of protoplanets. Resonances occur when the orbital period of a body is a simple fraction of the orbital period of a more massive object, such as a neighboring protoplanet or the central star. These resonances can concentrate planetesimals in certain regions, creating zones of enhanced collision probability and accretion. Conversely, some resonances can act as barriers, destabilizing orbits and preventing planetesimals from remaining in specific locations for long periods. The interplay of these effects contributes to the spatial structure of the emerging planetary system, influencing both the number and size distribution of protoplanets. In particular, resonances can help explain the presence of gaps, rings, and clusters observed in some protoplanetary disks, where material has been concentrated or cleared out by the gravitational influence of forming bodies. As protoplanets grow, their gravitational influence extends beyond simply capturing planetesimals. They begin to perturb the orbits of nearby bodies, creating dynamical interactions that can lead to scattering, orbital migration, or collisions. These interactions can trigger a second phase of growth known as oligarchic growth, in which a limited number of large protoplanets dominate their local regions, controlling the accretion of smaller bodies. Each oligarchic protoplanet clears its orbital neighborhood, sweeping up remaining planetesimals and stabilizing the system through gravitational dominance. The spacing and mass of these protoplanets are shaped by a combination of local disk density, the efficiency of accretion, and the dynamical interactions among neighboring bodies. Over time, this process produces a structured population of protoplanets with well-defined orbits, setting the stage for the final assembly of planets. The material composition of protoplanets is influenced by their location within the disk. In the inner regions, where temperatures are higher, protoplanets are likely to be composed primarily of refractory materials such as silicates and metals, while farther from the star, in cooler regions, icy components become more prevalent. This compositional gradient, combined with the mass distribution established during accretion, contributes to the diversity of planetary types observed in mature systems, from rocky terrestrial worlds close to the star to icy giants in the outer regions. Additionally, collisions during this stage can lead to partial melting, differentiation, and the development of layered structures within protoplanets, further enhancing their complexity and setting the stage for subsequent geological evolution. Dynamical friction, the process by which smaller bodies damp the motion of larger protoplanets, also plays a significant role in stabilizing growing bodies. As larger protoplanets interact gravitationally with the surrounding swarm of smaller planetesimals, their eccentricities and inclinations are reduced, allowing for more orderly growth. This effect enhances the likelihood of constructive collisions and promotes the formation of larger, more stable bodies over time. Combined with gravitational focusing, resonant interactions, and local variations in material density, dynamical friction ensures that protoplanet formation is both efficient and selective, favoring the growth of the most massive bodies while smaller planetesimals are either accreted or scattered. Observations of young planetary systems support this theoretical framework. Gaps and rings in protoplanetary disks, often detected through high-resolution imaging at millimeter and submillimeter wavelengths, suggest that protoplanets are actively shaping their surroundings. These features indicate regions of enhanced accretion, orbital clearing, and material concentration, consistent with the processes described in numerical models. Furthermore, the inferred masses of some embedded protoplanets suggest that significant growth can occur within the first few million years of disk evolution, confirming the efficiency of gravitationally driven accretion and resonant interactions. In summary, the formation of protoplanets is a complex interplay of gravitational accretion, collisional dynamics, and resonant interactions. Kilometer-sized planetesimals collide and merge, aided by gravitational focusing, while local disk conditions and dynamical evolution determine the efficiency and outcome of these interactions. Resonances influence the spatial distribution and growth patterns of emerging bodies, while processes such as dynamical friction stabilize orbits and facilitate orderly accretion. The result is the emergence of a population of protoplanets that dominate their local regions, exhibit compositional diversity, and form the foundation for the eventual assembly of planets. This stage transforms a population of individual planetesimals into structured, interacting bodies, bridging the gap between small solid building blocks and fully formed planets. The formation of gas giants marks one of the most dramatic transformations in a planetary system, as solid protoplanets evolve from primarily rocky or icy bodies into massive worlds enveloped by thick layers of hydrogen, helium, and other volatiles. This stage of planet formation is contingent upon the protoplanet reaching a critical mass, typically on the order of several Earth masses, sufficient to gravitationally attract and retain a substantial gaseous envelope from the surrounding protoplanetary disk. The accretion of gas is a complex interplay between the mass of the solid core, the local density and temperature of the disk, and the ability of the protoplanet to radiate away the energy released during gas capture. Initially, the protoplanet's gravity is modest, allowing it to slowly accumulate a tenuous atmosphere of hydrogen and helium. As the mass of the envelope increases, the gravitational potential deepens, and the rate of gas accretion accelerates. This phase is often described as runaway gas accretion, where the protoplanet rapidly transitions from a predominantly solid body to a gas-dominated giant. The conditions under which a protoplanet can capture gas are influenced by both the properties of the core and the characteristics of the surrounding disk. A more massive core produces a stronger gravitational pull, increasing the likelihood of retaining gas against thermal escape. Additionally, the temperature and density of the disk play a critical role. Cooler, denser regions provide more material for accretion and reduce the thermal energy that can drive gas away. In the inner regions of the disk, closer to the central star, high temperatures and lower gas densities make runaway gas accretion more difficult, favoring the formation of smaller, rocky planets. In contrast, in the outer disk where temperatures are lower and ice can condense, protoplanets can grow larger cores more quickly and capture substantial envelopes, explaining why gas giants are typically found farther from their stars. The presence of ices also enhances solid core growth by increasing the availability of accretable material, accelerating the timing of gas capture. The formation of gas giants contrasts sharply with the evolution of rocky terrestrial planets. Rocky planets grow primarily through the accretion of solid material and remain limited in size because the disk contains insufficient gas for them to acquire thick atmospheres, and their cores generally never reach the critical mass necessary for runaway gas accretion. Gas giants, on the other hand, benefit from both the growth of a solid core and the subsequent accumulation of massive gaseous envelopes, resulting in a fundamentally different planetary structure. This dichotomy leads to striking differences in density, composition, and overall mass between terrestrial and giant planets. Terrestrial planets are dense, rocky worlds with thin atmospheres, while gas giants are dominated by thick hydrogen-helium envelopes and often possess relatively small solid cores compared to their overall mass. The timing of formation is also crucial. Gas giants must acquire their envelopes while the protoplanetary disk still contains significant gas, a period typically limited to a few million years. If the disk disperses before the core reaches critical mass, the protoplanet may remain an ice giant or a massive terrestrial planet instead of a true gas giant. Mass and location within the disk both exert a strong influence on the final outcome of gas accretion. More massive cores attract gas more efficiently and can trigger runaway accretion earlier, allowing them to grow larger before disk dispersal limits further accumulation. Protoplanets forming in regions with higher disk surface density are more likely to grow massive cores, as they have greater access to solid material. Meanwhile, protoplanets in the outer disk benefit from the condensation of ices, which increase the effective solid mass available for core formation. In some cases, protoplanets can migrate inward or outward due to interactions with the disk, altering their gas accretion histories. Migration can deliver a growing giant into regions with higher or lower gas density, modifying the rate at which it accretes material and ultimately influencing its final mass and orbital location. This complex interplay between core mass, disk density, temperature, and migration dynamics helps explain the wide diversity of gas giant planets observed in both our solar system and exoplanetary systems. The structure of gas giant protoplanets evolves as they accrete gas. Initially, the atmosphere is diffuse and extended, with low density near the surface of the core. As accretion continues, the envelope contracts under its own gravity, increasing pressure and temperature near the core. This contraction releases gravitational energy, which must be radiated away to allow further gas inflow. Efficient cooling is therefore a critical factor in sustaining gas accretion. Protoplanets with higher luminosity due to energy released from solid accretion or contraction may slow the accumulation of gas. The final mass of the gas giant depends on a balance between the available disk material, the efficiency of energy dissipation, and the time remaining before disk dispersal. In some cases, gas giants may acquire multiple times the mass of Jupiter, while in other cases, accretion may be truncated, producing smaller Neptune-like worlds. Observational evidence supports these theoretical models. Surveys of exoplanets show a correlation between stellar distance and planetary type, with gas giants more commonly found beyond the snow line, the distance in the disk where water and other volatiles condense. Observations of young protoplanetary disks reveal gaps, spirals, and density waves consistent with the presence of accreting gas giants, suggesting that these planets are actively shaping their environments even during formation. The diversity of gas giant masses and compositions, including variations in core size and envelope fraction, reflects the sensitivity of gas accretion to local disk conditions, core properties, and timing. In summary, gas accretion and giant planet formation represent a pivotal phase in planetary system development. Protoplanets must grow massive solid cores, typically aided by the presence of ices and enhanced solid density in the outer disk, before they can capture substantial gas envelopes. The efficiency of gas accretion is influenced by the mass of the core, the thermal and density conditions of the disk, and the ability of the protoplanet to radiate away energy. Differences in formation location, mass, and timing account for the contrast between rocky and gas giant planets, explaining why terrestrial worlds dominate the inner regions of planetary systems, while massive gas giants are typically found farther out. Runaway gas accretion transforms initially solid bodies into massive, hydrogen-helium-dominated planets, shaping the architecture and diversity of planetary systems across the galaxy. Differentiation is a fundamental process in planetary evolution, transforming initially homogeneous protoplanets into layered worlds with distinct internal structures composed of cores, mantles, and crusts. This separation occurs as a result of gravitational energy, heat from accretion, radiogenic decay, and impacts, which together raise internal temperatures enough to partially or fully melt the material inside a planet. When temperatures reach the melting points of different minerals and metals, denser materials, primarily iron and nickel, sink toward the center, forming a metallic core, while lighter silicates rise to form a mantle. This process is driven by density contrasts, with heavy metals concentrating at the center and silicates and other lighter materials forming the surrounding layers. Differentiation is not instantaneous but occurs over millions of years, influenced by the size of the body, the amount of heat generated internally, and the timing of accretion. Larger bodies are more likely to differentiate completely due to their stronger self-gravity and higher capacity for retaining heat, while smaller planetesimals may remain partially or completely undifferentiated. The formation of a core is intimately linked to the development of a magnetic field. As the metallic core becomes partially liquid, convection can occur within the molten metal, generating electrical currents that give rise to a planetary dynamo. The efficiency of this dynamo depends on the composition, temperature, and convective vigor of the core. A planet with sufficient convective motion in its liquid outer core can sustain a long-lasting magnetic field, which serves as a protective shield against stellar winds and cosmic radiation. The presence of a magnetic field has profound implications for a planet's atmosphere and surface conditions, helping to prevent atmospheric stripping and contributing to the habitability of terrestrial planets. The onset of core formation is therefore a critical stage not only in structural differentiation, but also in the establishment of key planetary properties that influence long-term evolution. Radiogenic heating plays a crucial role in driving differentiation and internal activity. Radioactive isotopes, such as uranium-238, thorium-232, and potassium-40, decay within the planet's interior, releasing heat that contributes to melting and convective motion in both the mantle and core. This internal heat source operates alongside heat generated by the energy of accretion, which is released as kinetic energy from colliding planetesimals and protoplanets is converted into thermal energy. Large impacts during the late stages of accretion further contribute to heating, locally or globally melting planetary material and accelerating differentiation. In some cases, particularly massive impacts can strip away outer layers, trigger extensive magma oceans, or even reset differentiation processes, emphasizing the role of stochastic events in shaping a planet's internal structure. The mantle, formed from lighter silicate material, evolves through partial melting, convection, and chemical differentiation. Convection within the mantle facilitates the transport of heat from the interior to the surface, driving tectonic processes, volcanism, and the formation of a stable lithosphere. Mantle dynamics also influence the composition of the crust by transporting material upward, where partial melting produces magma that can solidify to form igneous rocks. Over time, these processes contribute to the establishment of a layered lithosphere, with variations in density and composition between crust and mantle. The mantle is not uniform. Compositional differences, phase transitions, and temperature gradients create zones with distinct physical and chemical properties that affect convection and planetary evolution. The crust represents the outermost layer of a differentiated planet and forms as a result of cooling and solidification of magma at the surface. The thickness, composition, and stability of the crust vary depending on planetary size, heat flow, and tectonic activity. On larger planets with active tectonics, crust is continuously recycled through subduction and volcanic resurfacing, whereas on smaller, geologically inactive bodies, the crust may remain largely unchanged for billions of years. The crust also plays a critical role in the retention of an atmosphere and the regulation of surface conditions. Its composition and structure influence the development of oceans, continents, and the long-term cycling of volatiles such as water and carbon dioxide. Differentiation and internal structure are influenced by both intrinsic and extrinsic factors. The timing and rate of accretion determine the amount of heat available for melting and core formation, while the chemical composition of the protoplanet dictates the density contrasts that drive separation. Extrinsic factors, such as the frequency and magnitude of impacts, also shape the final structure by adding energy and redistributing material. In addition, the location within the protoplanetary disk affects the composition of accreted material, influencing the relative abundances of metals, silicates, and volatiles that contribute to differentiation. Consequently, planets forming at different distances from their star or in different disk environments can exhibit a wide diversity of internal structures, magnetic properties, and thermal histories. Evidence for differentiation is observed throughout the solar system. Terrestrial planets such as Earth, Venus, and Mars show clear layered structures, with dense metallic cores, silicate mantles, and crusts of varying composition and thickness. Mercury, with its disproportionately large core, exemplifies how variations in initial composition and impact history can result in unique planetary structures. Icy bodies in the outer solar system, including some moons of Jupiter and Saturn, demonstrate that differentiation is not limited to rocky planets. Heating from radioactive decay, tidal forces, or early accretion can induce partial melting and the formation of layered interiors even in smaller, volatile-rich bodies. Differentiation also underpins many geological processes, from volcanism to tectonics, influencing planetary evolution over billions of years. In conclusion, differentiation transforms initially homogeneous protoplanets into complex, layered worlds with distinct cores, mantles, and crusts. This process is driven by internal heating from accretion, radiogenic decay, and impacts, and is critical for the development of magnetic fields, tectonic activity, and long-term planetary evolution. Mantle convection, core formation, and crustal development interact to create stable planetary structures while regulating heat flow, composition, and surface conditions. The diversity of differentiation outcomes across planetary bodies reflects variations in mass, composition, accretion history, and environmental context, highlighting its central role in shaping the structure, dynamics, and potential habitability of planets throughout the galaxy. Collisions have played a pivotal role in shaping the evolution of planets, dramatically influencing their physical, chemical, and orbital properties. From the earliest stages of planet formation, protoplanets and planetesimals frequently collided with one another, ranging from gentle mergers to catastrophic impacts. These collisions contributed to the accretion of mass, enabling bodies to grow from kilometer-sized planetesimals into fully fledged planets. However, not all collisions resulted in simple growth. High-energy impacts could fragment bodies, eject significant amounts of material, and even alter the spin and orbital characteristics of the affected planets. The energy released during these events often led to localized or global melting, producing magma oceans and accelerating differentiation. The scale and timing of collisions determined their consequences. Early-stage impacts helped shape the initial mass and structure of planets, while later, more stochastic collisions could reset or modify evolutionary pathways. One of the most significant periods of collisional activity in the solar system was the late heavy bombardment, a phase occurring approximately 4 to 3.8 billion years ago when the inner planets experienced an intense spike in impacts. This epoch is evidenced by the heavily cratered surfaces of the Moon, Mercury, and other terrestrial bodies, as well as isotopic dating of lunar samples. During this time, residual planetesimals, left over from the formation of the solar system, collided with terrestrial planets in massive numbers, delivering energy, material, and volatiles that influenced planetary geology and atmospheres. The late heavy bombardment not only reshaped planetary surfaces, but also affected interior dynamics by triggering widespread melting and potentially influencing mantle convection patterns. The impacts may have played a role in volatile delivery, contributing to the formation of early oceans and atmospheres, particularly on Earth. These collisional events highlight the interplay between external bombardment and internal evolution, showing that planetary development cannot be understood as an isolated, gradual process, but as a series of punctuated, often violent events. Collisions also played a critical role in the formation of moons and planetary ring systems. The leading hypothesis for the Moon's origin, for example, is the giant impact scenario, in which a Mars-sized body collided with the early Earth. This collision ejected a massive amount of debris into orbit around Earth, which eventually coalesced to form the Moon. The composition and isotopic similarity between Earth and lunar materials support this scenario, demonstrating how a single catastrophic collision can fundamentally alter the satellite architecture of a planetary system. Other moons in the solar system may have formed through similar processes, although many also result from gravitational capture or co-accretion within circumplanetary disks. Planetary rings, such as those around Saturn, are thought to have originated from the tidal disruption of moons or large planetesimals, showcasing another way in which collisions can create complex, persistent structures in planetary systems. Collisional processes thus not only contribute to planetary growth, but also to the formation of secondary systems that influence orbital dynamics and long-term evolution. The consequences of collisions are multifaceted and depend on the scale, velocity, angle, and composition of the impacting bodies. Low-velocity impacts tend to result in accretion, adding mass to the target body and potentially triggering localized melting. High-velocity or oblique impacts can generate extensive ejecta, cause mantle excavation, or even disrupt entire protoplanets, redistributing material throughout the planetary system. Collisions also influence the spin and tilt of planets. For instance, Uranus's extreme axial tilt is widely attributed to one or more massive impacts during its early history. The distribution of impact craters across planetary surfaces provides a historical record of collisional activity, offering insight into the timing, frequency, and scale of these events. On Earth, however, tectonic activity, erosion, and volcanism have erased much of the early impact record, making the Moon and Mercury particularly valuable for reconstructing the solar system's collisional past. Collisions contribute not only to physical transformation, but also to chemical evolution. The high temperatures generated during large impacts can melt and vaporize surface material, driving chemical differentiation, creating new mineral phases, and altering isotopic ratios. Volatile delivery during impacts is particularly important for planets like Earth, where comets and volatile-rich asteroids may have contributed significant amounts of water and other essential elements. Some impact events may even trigger transient atmospheres or release gases from the interior, modifying the composition and pressure of planetary envelopes. These chemical effects underscore how collisions intertwine with internal and atmospheric evolution, influencing habitability and surface conditions. Examples from the solar system illustrate the wide range of collisional outcomes. Mercury's large metallic core relative to its mantle is hypothesized to result from one or more giant impacts that stripped away significant portions of the original silicate shell. The Moon, as discussed, is a product of a massive impact that reshaped both Earth and the early solar system's satellite architecture. Mars bears the scars of numerous basins, such as the Hellas and Chryse impact sites, which influenced volcanic activity and potentially hydrological processes. On the outer planets, moons and ring systems like those of Saturn and Jupiter display evidence of collisional fragmentation and accretion, highlighting that impacts are not limited to terrestrial environments. Even small bodies, such as asteroids and comets, bear witness to this violent history, with cratered surfaces and fragmented structures preserving records of past collisions. Collisional processes are ongoing, although less frequent in modern times compared to the early solar system. Contemporary impacts provide insight into planetary dynamics and continue to influence planetary surfaces and atmospheres. Meteorites, for example, deliver material from other parts of the solar system, linking current small-scale collisions to the broader history of planetary formation. Studying collisions allows scientists to reconstruct the evolution of planetary systems, understand the mechanisms behind moon and ring formation, and assess the impact of stochastic, high-energy events on planetary structure, chemistry, and habitability. In conclusion, collisions and the late heavy bombardment have been central to planetary evolution, affecting growth, differentiation, orbital characteristics, and satellite formation. Catastrophic impacts shape the surfaces, interiors, and atmospheres of planets, while the dynamics of these events created moons, rings, and other secondary structures. The variety of outcomes, from minor accretionary impacts to planet-altering collisions, demonstrates the complex and violent processes underlying the evolution of planetary systems. By examining these events in the solar system, scientists gain insight into how collisions influence planetary formation, chemical evolution, and long-term development, revealing the essential role of impacts in sculpting the worlds we observe today. Atmospheres are a defining feature of planets, influencing climate, surface conditions, and the potential for life. The formation of a planet's atmosphere begins early in its evolution, during the accretion and differentiation phases. In the case of giant planets or sufficiently massive protoplanets, a primary atmosphere can be captured directly from the surrounding protoplanetary disk. This gaseous envelope is composed predominantly of hydrogen and helium, reflecting the composition of the nebular gas. The ability of a protoplanet to retain such an atmosphere depends on its mass, gravity, and location within the disk. Smaller, rocky planets forming closer to their star are generally unable to retain a primary hydrogen-helium atmosphere due to thermal escape driven by intense stellar radiation. In contrast, more massive bodies or those forming farther from the star can maintain these primordial gases, which can serve as the basis for further atmospheric evolution. For terrestrial planets, secondary atmospheres emerge after the initial nebular gas is lost, largely through processes such as thermal escape, photoevaporation, and collisions with planetesimals. Outgassing during differentiation and volcanic activity is a major source of these secondary atmospheres. As magma oceans cool and the mantle solidifies, volatile compounds trapped within the interior, including water, carbon dioxide, nitrogen, and sulfur species, are released into the atmosphere. Large impacts can also contribute volatiles by delivering water and other gases from icy bodies such as comets or volatile-rich asteroids. The timing and intensity of these contributions shape the composition, density, and pressure of the developing atmosphere. On early Earth, for example, Volcanic outgassing and cometary impacts likely combined to provide water vapor and carbon dioxide, setting the stage for ocean formation and the eventual emergence of a hydrological cycle. The evolution of planetary atmospheres is influenced by the interplay between internal processes and external factors. Volcanism continues to regulate atmospheric composition long after the initial outgassing phase, replenishing gases and modifying chemical balances. Plate tectonics, present on Earth and potentially other terrestrial planets, recycles carbon and other volatiles between the mantle and surface, maintaining long-term climate stability. Impacts during periods of heavy bombardment can strip portions of the atmosphere, alter its composition, or temporarily increase surface temperatures through the release of energy. The presence of water and other condensable volatiles can further modify atmospheric dynamics, contributing to cloud formation, precipitation, and surface reservoirs that interact with both the interior and the exosphere. External factors, particularly stellar radiation and the solar wind, play a crucial role in shaping atmospheric retention and evolution. Ultraviolet radiation from the host star can break molecular bonds, leading to the loss of lighter gases such as hydrogen and helium. Charged particles in the solar wind can erode an unprotected atmosphere over time, as observed on planets without strong magnetic fields. Mars provides a clear example, where the combination of weak gravity and the absence of a global magnetic field allowed much of its early atmosphere to escape into space, leaving a thin, tenuous envelope today. In contrast, Earth's magnetic field protects the atmosphere by deflecting charged particles, helping to preserve its density and composition over billions of years. The coupling of internal dynamo-generated magnetic fields with atmospheric processes thus becomes critical for long-term habitability. Atmospheric composition varies widely across the solar system, reflecting differences in planetary mass, location, accretion history, and chemical inventory. Gas giants retain thick, hydrogen, and helium-dominated envelopes enriched with heavier elements from accreted solids, while ice giants contain more volatile ices such as methane, ammonia, and water within their atmospheres. Terrestrial planets display secondary atmospheres shaped by outgassing, impacts, and photochemistry, with compositions ranging from carbon dioxide-rich environments on Venus and Mars to the nitrogen and oxygen-dominated mixture on Earth. These differences influence surface conditions, greenhouse effects, temperature profiles, and climate evolution, demonstrating that atmosphere formation is not a uniform process, but a product of planetary-specific histories. Volatile delivery from icy bodies is particularly important for developing oceans and sustaining habitable conditions on terrestrial planets. Comets and asteroids, originating from outer regions of the planetary system, can transport water, carbon compounds, and other critical elements to the inner planets. The timing and magnitude of this delivery, combined with internal outgassing, determine the availability of surface liquids and the chemical composition of the early atmosphere. The retention of these volatiles is influenced by planetary gravity, surface temperature, and magnetic shielding, with larger, magnetically active planets more likely to maintain substantial reservoirs over geological timescales. Photochemistry and atmospheric circulation further refine the structure and composition of planetary atmospheres. Ultraviolet radiation drives chemical reactions that generate or destroy atmospheric constituents, such as ozone or molecular oxygen, influencing the stability of gases and the protection of the surface from harmful radiation. Atmospheric dynamics, including convection, circulation cells, and jet streams, distribute heat and material, shaping climate patterns and surface conditions. The presence of clouds and aerosols modifies the energy balance, reflecting or trapping radiation and interacting with the hydrological cycle. Over time, These processes interact with internal geological activity and external stellar influences to create complex, evolving atmospheres with distinct chemical, thermal, and pressure profiles. The study of atmospheric formation provides insight into planetary habitability and long-term evolution. By understanding the processes that govern the retention and loss of gases, the interplay between internal and external mechanisms, and the delivery of volatiles, scientists can reconstruct the histories of planets in our solar system and beyond. The diversity observed, from dense, hot Venusian envelopes to thin Martian atmospheres and Earth's life-sustaining balance, illustrates the critical role that atmospheric evolution plays in determining planetary environments. Each planet's atmosphere is a dynamic record of its formation, internal activity, and interactions with the surrounding space environment, highlighting the complex, interdependent processes that shape worlds across the cosmos. In conclusion, atmospheric formation begins with the capture of primary nebular gas on massive protoplanets and transitions to secondary atmospheres produced by outgassing, volcanism, and volatile delivery. These atmospheres evolve under the influence of internal activity, stellar radiation, impacts, and magnetic shielding, leading to a wide diversity of compositions and structures across planets. The interactions between these factors determine climate, surface conditions, and habitability, making atmospheric processes central to the long-term evolution of planets. Understanding these mechanisms illuminates not only the history of Earth and its neighbors, but also the potential characteristics of exoplanets throughout the galaxy. Planets are constantly exposed to radiation from their host star and the charged particles of the solar wind, both of which play a significant role in shaping their atmospheres, surfaces, and long-term evolution. High-energy photons, particularly in the ultraviolet and X-ray ranges, can interact with atmospheric molecules, breaking chemical bonds and initiating photochemical reactions. This process, known as photodissociation, can lead to the formation of new molecular species while simultaneously contributing to the loss of lighter elements, such as hydrogen and helium, from the atmosphere. On planets with weak gravity or limited magnetic protection, these processes can strip away substantial portions of the atmosphere over geological timescales, altering the overall chemical composition and influencing surface conditions. The effects of radiation are especially pronounced for planets close to their star, where stellar flux is intense and atmospheric escape processes are more efficient. The solar wind, a stream of charged particles emitted by the star, interacts with planetary atmospheres and magnetospheres in complex ways. On planets without strong magnetic fields, such as Mars, the solar wind can directly erode the upper atmosphere through a process called sputtering. In sputtering, energetic particles collide with atmospheric atoms and molecules, knocking them into space and contributing to gradual atmospheric thinning. This effect, combined with photodissociation and thermal escape, can drastically alter the mass and composition of an atmosphere over billions of years. In contrast, planets with active magnetic fields, like Earth, are partially shielded from the direct effects of the solar wind. The magnetic field deflects charged particles, creating a protective magnetosphere that prevents the majority of high-energy solar particles from reaching the surface. This protection is critical for maintaining a stable atmosphere, preserving volatile compounds, and reducing the impact of radiation on potential biospheres. Radiation and solar wind also play an important role in shaping surface chemistry. High-energy photons and particles can drive chemical reactions in surface minerals and ices, altering their composition and producing new compounds. On icy bodies and planets with frozen volatiles, ultraviolet radiation can trigger photochemistry that leads to the formation of complex organics, potentially contributing to prebiotic chemistry. Similarly, cosmic rays, which are highly energetic particles originating outside the solar system, can penetrate planetary surfaces and atmospheres, inducing molecular changes and forming isotopic signatures that record the planet's exposure history. In addition, the continuous bombardment by energetic particles contributes to weathering and surface modification, particularly on airless or thinly atmosphered bodies, such as Mercury or the Moon, where radiation-driven processes dominate over erosion by fluids or winds. The interaction between radiation, solar wind, and planetary magnetic fields can also produce spectacular electromagnetic phenomena, such as auroras. When charged particles are guided by magnetic field lines into polar regions, they collide with atmospheric atoms and molecules, exciting them and producing visible light emissions. Auroras not only serve as visible evidence of these interactions, but also provide insight into the structure of the magnetosphere, atmospheric composition, and the intensity of stellar activity. The strength and extent of such phenomena depend on the planet's magnetic field configuration, the density of the atmosphere, and the intensity of incoming particles. Over time, these interactions influence the retention of lighter elements, redistribute energy in the upper atmosphere, and contribute to long-term chemical and thermal evolution. The loss of light elements due to radiation and solar wind has profound consequences for atmospheric composition and planetary evolution. Hydrogen, being the lightest element, escapes most readily, and with it, compounds such as water vapor can be lost indirectly. On early Venus and Mars, for instance, evidence suggests that substantial water loss occurred through photodissociation of H2O and subsequent hydrogen escape, leaving behind oxidized atmospheres rich in heavier gases like carbon dioxide. On Earth, the presence of a strong magnetic field prevented similar catastrophic losses, allowing water and other volatiles to persist, shaping the development of oceans and a stable climate. The interplay between atmospheric escape and replenishment from volcanic outgassing, cometary impacts, and chemical recycling thus determines long-term habitability and surface conditions. Solar radiation also influences the thermal structure and dynamics of planetary atmospheres. Absorption of ultraviolet and visible light heats the upper layers of the atmosphere, creating temperature gradients that drive circulation patterns, winds, and convection. This energy input affects cloud formation, precipitation, and climate stability, particularly on planets with substantial atmospheres. Additionally, the photochemical production of compounds such as ozone can regulate surface UV flux, protecting biological material while influencing the overall energy balance of the planet. In this way, radiation not only modifies chemical composition but also shapes climate systems and geological processes, interacting with internal heat sources and planetary rotation to create complex atmospheric behavior. The presence and strength of a planetary magnetic field are therefore critical in mediating the effects of radiation and the solar wind. Magnetic fields are generated by the motion of conductive material in a planet's interior, typically in a liquid metallic core through dynamo action. A strong magnetic field provides a shield that preserves the atmosphere, maintains surface habitability, and reduces chemical alterations caused by energetic particles. Planets without such protection experience accelerated atmospheric erosion, altered surface chemistry, and potentially harsher conditions for life. This highlights the interconnected nature of planetary interiors, magnetic field generation, and external radiation processes in determining long-term evolution. Examples across the solar system illustrate these principles. Mercury, with a weak magnetic field and proximity to the Sun, experiences significant solar wind interaction, leading to surface sputtering and the formation of a thin exosphere. Mars, lacking a global magnetic field, lost much of its early atmosphere due to combined solar wind erosion and photodissociation. Earth, in contrast, retains a dense atmosphere and surface water largely because of its protective magnetosphere, demonstrating the critical role of magnetic shielding in preserving planetary environments. Venus, while possessing a thick atmosphere, lacks a global magnetic field, yet its dense CO2 envelope provides some protection against solar wind stripping, though the planet still suffers from hydrogen loss and extreme greenhouse effects. In conclusion, radiation and solar wind are major external forces shaping planetary evolution. They drive atmospheric escape, photochemistry, and surface alteration, while magnetic fields provide critical protection that influences retention of volatiles, climate stability, and habitability. The balance between these processes determines the long-term composition, structure, and dynamics of planetary atmospheres and surfaces. Understanding these interactions is essential for reconstructing the histories of planets in the solar system and for assessing the potential environments of exoplanets exposed to varying levels of stellar radiation and particle flux. The cooling of a planet after its initial formation is a fundamental process that drives the stabilization of its surface, the development of tectonic activity, and the emergence of oceans and land masses. After the accretion and differentiation phases, planets retain significant internal heat from multiple sources, including gravitational energy released during accretion, radioactive decay of isotopes such as uranium, thorium, and potassium, and energy from large impacts. This internal heat maintains partially molten interiors, driving convection within the mantle and facilitating the gradual crystallization of minerals. As the mantle cools, solid rock begins to form a rigid lithosphere that overlies the more ductile asthenosphere, providing the structural foundation for the development of tectonic plates and the surface features we recognize as continents and ocean basins. The rate of cooling is influenced by planetary size, composition, and the initial amount of heat retained from formation, with larger planets generally cooling more slowly due to their lower surface area-to-volume ratio. The crystallization of the mantle plays a pivotal role in the chemical and physical differentiation of the planet. As magma cools, heavier elements such as iron and nickel tend to sink toward the core, while lighter silicates rise to form the mantle and crust. This process not only establishes the internal stratification of the planet, but also generates compositional diversity within the crust, which later contributes to the formation of continents and volcanic activity. Partial melting in the mantle produces magmas that ascend through the lithosphere, creating volcanic eruptions and new crustal material at the surface. Over time, repeated cycles of melting, solidification, and volcanic resurfacing gradually stabilize the planetary surface, transforming it from a chaotic, molten environment into a more structured and layered landscape capable of supporting oceans and continents. Tectonic activity is closely linked to internal cooling and mantle convection. As the mantle loses heat, convective currents develop, driving the motion of rigid plates at the surface. This plate tectonic system is responsible for the creation and destruction of crustal material, the formation of mountain ranges, and the development of subduction zones and mid-ocean ridges. On planets like Earth, plate tectonics facilitates the recycling of elements, including water and carbon, between the interior and the surface, contributing to long-term climate regulation and the maintenance of habitable conditions. Even on planets without active plate tectonics, the cooling of the lithosphere can produce significant geological features, such as large volcanic provinces, rift valleys, and fault systems, demonstrating that the process of cooling and surface stabilization is universal, though its expression varies with planetary size, composition, and internal dynamics. The formation of oceans is intimately tied to the thermal evolution of the planet and the stabilization of the crust. As the surface cools, water vapor released by outgassing from volcanic activity begins to condense, forming the earliest bodies of liquid water. The cooling of the lithosphere allows these bodies to accumulate and coalesce into oceans, providing a stable reservoir for water and establishing the conditions necessary for erosion, sedimentation, and the cycling of nutrients. The presence of oceans further influences heat transport, as the circulation of water redistributes thermal energy across the surface, moderates climate, and interacts with the atmosphere to drive weather patterns and precipitation cycles. In addition, oceans act as sinks for carbon dioxide and other gases, chemically interacting with the crust and atmosphere to regulate planetary habitability over geological timescales. Land masses emerge as a result of crustal thickening, volcanic uplift, and the movement of tectonic plates. The interaction between rising magmas and the cooling lithosphere produces continental crust, which is less dense than oceanic crust and therefore remains elevated above the surrounding sea level. Erosion, sediment deposition, and tectonic activity shape the topography of these landmasses, creating mountains, valleys, and plateaus. The juxtaposition of oceans and continents establishes diverse environments that influence climate, erosion, and the cycling of elements between the surface and interior. Over time, the stabilization of these landmasses provides a platform for further geological and potentially biological processes, setting the stage for the development of ecosystems once conditions permit. The interplay between cooling, tectonics, and surface stabilization is not limited to Earth. Other planets and moons in the solar system provide illustrative examples of how these processes manifest under different conditions. Venus, for instance, shows evidence of extensive volcanic resurfacing and limited tectonic activity, reflecting a thermal evolution that maintains a hot interior and a lithosphere that behaves differently from Earth's plate tectonics. Mars, in contrast, has a largely static lithosphere today, but features such as Olympus Mons and ancient valley networks suggest a past in which cooling, volcanism, and crustal deformation played major roles in shaping its surface. Even icy moons, such as Europa and Enceladus, demonstrate that internal heat and surface crystallization influence the development of tectonic-like activity in ice shells, highlighting the universality of thermal processes in planetary evolution. The timing of cooling and surface stabilization influences atmospheric retention and climate. As the surface solidifies and oceans form, volatile gases released from the interior can accumulate in the atmosphere without being immediately lost to space. Cooling also allows for the development of magnetic fields, as the dynamo in the core may become more organized and capable of sustaining a protective shield. This combination of stabilized surface, oceans, and magnetic protection creates favorable conditions for long-term habitability and the potential emergence of life. The balance between heat loss, crustal dynamics, and surface evolution thus determines whether a planet achieves a stable configuration conducive to sustaining liquid water and maintaining atmospheric and geological processes over billions of years. In conclusion, planetary cooling is a critical driver of surface stabilization, tectonic activity, and the formation of oceans and land masses. Crystallization of the mantle and crust establishes the structural framework of the planet, while mantle convection drives tectonics and volcanic resurfacing. Cooling enables the condensation of water and the development of oceans, which interact with the lithosphere and atmosphere to regulate climate and chemical cycles. The emergence of continents and landforms provides topographical diversity and a platform for further geological and potentially biological evolution. Across planets, moons, and other planetary bodies, The processes of cooling and surface stabilization illustrate the intricate connection between internal heat, crustal development, and surface habitability, shaping the physical and chemical environment of worlds throughout the cosmos. The presence and evolution of gas giant planets exert a profound influence on the formation and long-term dynamics of interterrestrial planets, shaping their orbits, collision histories, and overall architecture within a planetary system. Gas giants, due to their immense mass and gravitational reach, act as both shepherds and disruptors of the surrounding disk of planetesimals, protoplanets, and smaller debris during the early stages of planetary formation. Their gravitational influence can alter the trajectories of nearby objects, leading to changes in orbital eccentricity, inclination, and stability. These interactions can either stabilize or destabilize regions of the protoplanetary disk, creating zones where inner planets are more likely to accrete steadily and other regions where collisions are frequent and disruptive. In essence, the position and mass of gas giants play a critical role in determining the architecture of the interplanetary system, influencing not only the formation of Earth-like planets, but also the likelihood of catastrophic impacts or the clearing of debris from the system. In the early solar system, Jupiter and Saturn were particularly influential due to their proximity and immense gravitational fields. Jupiter, as the largest planet, created strong perturbations in the surrounding disk, which helped shape the formation and orbital configuration of Mars, the asteroid belt, and ultimately the inner terrestrial planets. Its gravitational influence acted as a barrier, limiting the inward migration of planetesimals from the outer solar system and effectively protecting the inner planets from excessive bombardment by icy bodies. At the same time, Jupiter's presence could redirect certain planetesimals inward, increasing the likelihood of high-energy impacts on Earth and Venus, which contributed to surface modification, volatile delivery, and potentially the seeding of prebiotic material. Saturn, positioned further from the Sun, complemented Jupiter's gravitational effects by influencing the outer edge of the interplanetary region and modifying the distribution of material in the asteroid belt. The interplay between these two gas giants created a delicate balance that shaped the dynamical environment in which Earth formed, highlighting the importance of massive planets in regulating the formation conditions of smaller, potentially habitable worlds. One of the key mechanisms by which gas giants affect inner planets is the gravitational scattering of planetesimals. As protoplanets and smaller bodies migrate within the disk, encounters with a massive planet like Jupiter can dramatically alter their trajectories. Some objects may be ejected entirely from the planetary system, becoming interstellar travelers, while others may be captured into new orbits, either as stable companions or temporary bodies that eventually collide with inner planets. This process has multiple consequences. It can reduce the density of debris in certain regions, lowering collision rates for forming terrestrial planets. Or conversely, it can inject high-velocity impactors into the inner system, contributing to episodes of heavy bombardment. The late heavy bombardment period in the solar system, for instance, is thought to have been influenced by the migration and resonance interactions of Jupiter and Saturn, which destabilized populations of planetesimals and comets, delivering material to the inner planets and playing a major role in their geological and atmospheric evolution. The gravitational effects of gas giants also influence orbital resonances, which can either stabilize or destabilize inner planet formation. When the orbital period of a small body forms a simple ratio with that of a giant planet, resonances can occur, leading to periodic gravitational perturbations. Such resonances can clear certain regions of material, as in the case of Kirkwood gaps in the asteroid belt caused by Jupiter's resonances, or they can concentrate material into specific regions, promoting the formation of larger protoplanets. Resonances not only affect the spatial distribution of planetesimals, but also impact the timing and frequency of collisions in the inner disk, thereby shaping the size distribution, composition, and orbital eccentricity of emerging terrestrial planets. These gravitational interactions underline the complex and indirect role of gas giants in determining the habitability potential of inner worlds by modulating their bombardment history and orbital stability. Gas giants also act as a shield for inner planets by capturing or redirecting comets and asteroids. Objects that might otherwise strike a young Earth can be intercepted by a giant planet, either colliding with it or being slung into distant orbits. This protective role reduces the frequency of catastrophic impacts, which might otherwise sterilize surfaces or strip atmospheres. At the same time, Jupiter and Saturn are responsible for delivering critical materials, such as water and volatile compounds, from the outer solar system. Icy bodies scattered inward by gravitational interactions can collide with terrestrial planets, supplying essential components for oceans, atmospheres, and the potential development of life. The dual role of gas giants, as both protectors and suppliers of material, illustrates the nuanced influence they have on the evolution of inner planets. The migration history of gas giants also plays a critical role in inner planet evolution. If a giant planet migrates inward significantly, it can disrupt the orbits of forming terrestrial planets, clearing regions of the disk and preventing stable planet formation. Conversely, moderate migration or relatively stationary giant planets create a more predictable environment, allowing inner planets to accrete and stabilize over time. The specific pattern of migration, combined with mass and resonance interactions, determines the likelihood that inner planets survive intact, develop stable orbits, and accumulate volatile materials necessary for habitability. This explains why the configuration of gas giants in exoplanetary systems is often correlated with the presence, size, and stability of terrestrial planets closer to the host star. In the context of Earth's history, the influence of Jupiter and Saturn was instrumental. Their gravitational interactions helped maintain a relatively stable inner solar system, reducing catastrophic collisions while still delivering sufficient water and volatiles to Earth. These processes contributed to the formation of a habitable environment, with a stable orbit, moderate impact frequency, and availability of essential materials for oceans and atmosphere. By shaping the distribution of asteroids and comets, the gas giants indirectly influenced Earth's geological, atmospheric, and biological evolution, demonstrating that the fate of terrestrial planets is intimately tied to the presence and dynamics of massive planetary neighbors. In conclusion, gas giant planets exert a multifaceted influence on inner terrestrial planets through their gravitational forces, orbital resonances, and ability to scatter or capture smaller bodies. They shape the distribution of material, modulate collision rates, deliver essential volatiles, and protect inner planets from extreme bombardment. The specific mass, position, and migration history of giants such as Jupiter and Saturn in our solar system exemplify how massive planets can stabilize interplanetary environments, facilitate the accumulation of water and organics, and ultimately contribute to the habitability of worlds like Earth. Understanding these interactions provides crucial insight into planetary system architecture and the factors that determine the formation and long-term evolution of potentially habitable planets throughout the galaxy. The formation of conditions suitable for life on a planet is a complex interplay between atmospheric stability, the presence and cycling of water, geological activity, and magnetic protection. After a planet has cooled and its surface has stabilized, the next critical step in establishing habitability involves the development of an atmosphere capable of supporting liquid water and shielding the surface from harmful radiation. The atmosphere initially forms from the outgassing of volatile compounds during volcanic activity, supplemented by the delivery of water, carbon dioxide, ammonia, and other molecules from icy planetesimals and comets. Volcanic eruptions release gases trapped in the mantle, including water vapor, carbon dioxide, nitrogen, and trace elements, which accumulate to form a primary atmosphere. Over time, processes such as condensation, chemical reactions, and photodissociation shape this atmosphere, leading to the stabilization of pressure, temperature, and composition at levels suitable for liquid water to exist on the surface. The retention of a stable atmosphere depends on several factors, including the planet's gravity, the presence of a magnetic field to protect against stellar winds, and the ongoing balance between outgassing and atmospheric loss. Water circulation is another critical factor in the development of habitable conditions. As a planet cools and oceans form, water begins to cycle through evaporation, precipitation, runoff, and infiltration into the crust. This hydrological cycle distributes heat across the planet, moderates climate, and supports chemical reactions that are essential for life. Water acts as a solvent, enabling the dissolution and transport of minerals and nutrients from rocks to the oceans and surface environments. In addition, interactions between water and the crust create chemical gradients and energy sources that can support prebiotic chemistry. The delivery of water from external sources, such as icy bodies scattered by giant planets, complements endogenous sources from outgassing, ensuring sufficient reservoirs for oceans, lakes, and groundwater. Over geological timescales, the persistence of liquid water is closely tied to the planet's thermal evolution, atmospheric pressure, and climate feedback mechanisms, all of which determine whether life-supporting conditions can be maintained. Chemical cycles on a planet are intricately connected to both water and geological activity. The carbon cycle, for instance, regulates atmospheric carbon dioxide through processes such as volcanic outgassing, weathering of rocks, and deposition of carbonates in oceans. Weathering reactions remove CO2 from the atmosphere and transport it into the oceans, where it combines with dissolved minerals to form carbonate rocks, which can later be subducted into the mantle through tectonic activity. This long-term cycling stabilizes climate and maintains temperature ranges conducive to liquid water, creating a relatively steady environment in which life can emerge. Other elemental cycles, including those of nitrogen, sulfur, and phosphorus, rely on both chemical reactions in water and geological recycling through volcanism, erosion, and subduction. These cycles establish the availability of essential nutrients and maintain chemical balance, supporting the metabolic processes that sustain living organisms once they emerge. Geological activity plays a crucial role in creating and sustaining habitable conditions. Plate tectonics, volcanic eruptions, and crustal deformation contribute to the recycling of nutrients, regulation of surface temperature, and maintenance of diverse habitats. Volcanism releases gases and minerals into the atmosphere and oceans, replenishing key chemical components, while tectonic processes drive the uplift of land masses, the creation of ocean basins, and the formation of hydrothermal systems. Hydrothermal vents, in particular, provide localized energy and chemical gradients that can support microbial life and potentially act as cradles for early life forms. Geological activity also helps prevent atmospheric stagnation, ensuring that gases essential for life are replenished and that surface conditions do not become chemically depleted. Without ongoing geological processes, a planet's surface and oceans may become inhospitable, with limited chemical diversity and diminished capacity to support life. The presence of a magnetic field significantly enhances the habitability of a planet by protecting the atmosphere and surface from stellar radiation and charged particles. A planetary dynamo, generated by the movement of conducting materials within the core, creates a magnetic shield that deflects harmful solar wind and cosmic rays. This protection prevents the gradual erosion of the atmosphere and the stripping of water from the surface, helping maintain stable conditions for life. Magnetic fields also reduce the intensity of surface radiation, creating a safer environment for emerging organisms and preserving delicate chemical compounds necessary for prebiotic chemistry. The interplay between a convecting interior rotation rate and core composition determines the strength and longevity of the magnetic field, which in turn influences the long-term habitability of the planet. Temperature stability is also central to the formation of conditions for life. A combination of a stable orbit, sufficient atmospheric greenhouse effect, and energy distribution via water and atmospheric circulation ensures that surface temperatures remain within a range suitable for liquid water. Planets with highly eccentric orbits, thin atmospheres, or insufficient heat transport may experience extreme temperature fluctuations that hinder the formation of stable oceans and the persistence of life-supporting environments. Climate feedback mechanisms, including the greenhouse effect, cloud formation, and ocean circulation, further regulate surface conditions, moderating the effects of variations in solar radiation or volcanic activity. The interaction between all these factors, stable atmosphere, water circulation, chemical cycling, geological activity, and magnetic protection, creates a self-regulating system that can sustain habitable conditions over billions of years. Each element reinforces the others. Geological activity replenishes atmospheric gases. Water facilitates chemical reactions. The atmosphere regulates temperature, and the magnetic field protects both water and atmosphere from erosion. This synergy lays the foundation for the emergence of life, providing stable environments, chemical energy, and essential nutrients. Early Earth, for example, exemplifies how these processes combine to create a planet capable of supporting life, with oceans, active tectonics, a stable climate, and a protective magnetic field. In conclusion, the formation of conditions suitable for life is the result of a delicate balance between multiple planetary processes. A stable atmosphere provides the baseline for climate regulation and water retention, while the hydrological cycle enables nutrient transport and energy distribution. Geological activity ensures chemical replenishment and dynamic surface environments, and a magnetic field shields the planet from harmful radiation. Together, these processes establish a framework for long-term habitability, demonstrating that the emergence of life is contingent upon the interconnection of atmospheric, hydrospheric, lithospheric, and magnetospheric systems. Planets that successfully integrate these factors create the environmental stability necessary for life to take hold, persist, and evolve over geological timescales. Modern methods of studying planet formation combine observational astronomy, theoretical modeling, and laboratory experiments to create a comprehensive understanding of how planets emerge from cosmic dust and gas. Observational techniques have advanced dramatically over the past few decades, driven by the development of powerful ground-based telescopes and space-based observatories. Instruments such as the Atacama Large Millimeter/Submillimeter Array, ALMA, the Hubble Space Telescope, and the James Webb Space Telescope allow astronomers to peer into protoplanetary disks surrounding young stars, capturing detailed images of dust and gas structures where planets are forming. By observing these disks at multiple wavelengths, researchers can infer the temperature, density, composition, and dynamics of the material. Submillimeter and infrared observations are particularly valuable for studying the cooler outer regions of disks where ice-rich planetesimals and gas giants are likely to form. High-resolution imaging can reveal gaps, rings, and spiral structures within disks, which often indicate the presence of growing planets influencing their environment through gravitational interactions. Observations of these features provide direct evidence of ongoing planet formation and offer benchmarks for testing theoretical models. In addition to direct imaging, spectroscopic methods are essential for analyzing the chemical composition of disks and forming planets. By examining the emission and absorption lines of various molecules, astronomers can determine the abundance of silicates, metals, ices, and complex organic compounds. These measurements inform our understanding of the initial building blocks of planets and the processes that lead to differentiation between rocky and gaseous planets. Observations of isotopic ratios, such as deuterium to hydrogen in water, can trace the origin of volatiles and the contribution of comets or icy planetesimals to the development of habitable worlds. Combining spatially resolved imaging with spectroscopy allows scientists to construct three-dimensional models of disks, mapping temperature gradients, chemical distributions, and regions of turbulence or dust accumulation. These observational data are crucial for identifying the conditions under which planetesimals grow into protoplanets and eventually into fully formed planets. Theoretical modeling plays an equally important role in studying planet formation, allowing scientists to simulate complex processes that cannot be observed directly. Computational models range from small-scale simulations of dust-grain collisions and coagulation to large-scale hydrodynamic simulations of entire protoplanetary disks. Models of dust aggregation examine how microscopic particles stick together through electrostatic forces, van der Waals interactions, or surface chemistry, providing insight into the formation of planetesimals. At larger scales, in-body simulations track the gravitational interactions between growing protoplanets, gas, and planetesimals, revealing how orbital resonances, collisions, and scattering events shape planetary systems. Hydrodynamic models of gas disks study how turbulence, pressure gradients, and disk instabilities influence the accretion of gas onto forming giant planets and the migration of planets within the disk. By comparing simulation results with observational data, researchers can validate theories, refine parameters, and explore alternative scenarios for planetary system architecture. Laboratory experiments complement observational and theoretical approaches by reproducing the physical and chemical conditions of planet formation on a small scale. Experiments with dust analogs allow scientists to study the mechanisms of particle aggregation under microgravity conditions, simulating the early stages of planetesimal formation. Experiments on gas-solid interactions, ice sublimation, and chemical reactions under protoplanetary disk conditions provide valuable data on the stability and evolution of molecules that will eventually become part of planetary atmospheres or surfaces. High-pressure and high-temperature experiments recreate the internal conditions of differentiating protoplanets, revealing how metals separate from silicates to form cores and how volatile compounds behave under extreme conditions. Laboratory studies of impact processes shed light on the consequences of collisions between planetesimals, including fragmentation, melting, and the delivery of water and organics. These experimental results provide crucial input for models, helping to constrain the physical parameters and chemical pathways involved in planet formation. The study of exoplanetary systems has opened a new frontier in understanding planet formation by offering a broader statistical perspective beyond the solar system. Thousands of exoplanets have been discovered using methods such as the transit technique, radial velocity measurements, direct imaging, and microlensing. These observations reveal a remarkable diversity in planetary sizes, compositions, orbital configurations, and stellar environments. By comparing these exoplanetary systems with the architecture of our solar system, scientists can test the universality of planet formation processes and identify factors that influence planet types and system stability. Observations of tightly packed systems, hot Jupiters, super-Earths, and planets in binary star systems challenge traditional models and prompt the development of new theoretical frameworks to explain these diverse outcomes. The comparative study of exoplanets also informs our understanding of habitability, water delivery, and the frequency of Earth-like planets in the galaxy. Machine learning and data-driven approaches are increasingly integrated into observational and modeling efforts. Large data sets from telescopes, surveys, and simulations require advanced algorithms to detect subtle signals, classify disk structures, and predict evolutionary outcomes. Machine learning helps identify correlations between disk properties, stellar characteristics, and planet formation outcomes, enabling more efficient exploration of the vast parameter space involved in planetary systems. By combining statistical analysis with physical modeling, researchers can prioritize observational targets, refine theoretical predictions, and uncover hidden patterns in complex planetary formation processes. In summary, modern studies of planet formation rely on a synergy of observational astronomy, theoretical modeling, laboratory experiments, and comparative exoplanetary studies. Observations provide direct evidence of disk structures, composition, and dynamics, while spectroscopy uncovers the chemical building blocks of planets. Computational models simulate dust aggregation, protoplanet evolution, and disk-planet interactions, bridging the gap between small-scale physics and large-scale system architecture. Laboratory experiments validate physical and chemical mechanisms, offering constraints for models and insights into processes that cannot be observed directly. Exoplanet surveys expand the scope of investigation, revealing the diversity of planetary systems and allowing comparisons that refine our understanding of universal versus local formation mechanisms. Emerging techniques, such as machine learning, further enhance the ability to process complex data and predict outcomes, making the study of planet formation a highly integrated, interdisciplinary field. By combining these approaches, scientists are steadily uncovering the intricate journey from cosmic dust to fully formed worlds, providing unprecedented insight into the origins of planets, including Earth, and the conditions that allow them to sustain life. Good night.